Okay. Can everybody see the slides?
Yep.
Is the transition well?
Yep.
Okay, great. So let's start. So first of all, maybe you have noticed that we have released our last homework 5, on last Thursday, and also we made notice about final report due. It should be May 7th. That is the weekend of the, I guess it's Friday, right? Friday of the final exam. So we want to allocate extra time after the final exam so that you have at least 4 days to finish the final project report. So that should be sufficient. So what I just want to emphasize is that please start doing homework 5 as soon as possible, since we have finished the neural network topic. So the major focus of homework 5 is about neural network topics. So if you're familiar with, if you're comfortable with like back propagation, all kinds of details, that should be pretty easy for you. And of course, if you're interested in trying PyTorch or TensorFlow, there is a big bonus problem in that homework. And then today we're gonna talk about logistic regression, and then they should have enough knowledge to do all the homework problems for homework 5. Okay. Um, so any question regarding the schedule?
Yeah, do you know off the top of your head when the final exam is?
Oh, yeah, that's a good question. I plan to talk about that at on next Tuesday, our last lecture. But
Sure.
it's fine. We briefly talk about right now. So it's basically an online exam on Canvas. So it's pretty honest. It's pretty easy, open book, and most of the problems are single choices or multiple choices. A few text description problem, you're now required to write down complex formulas or mathematics, but you do need to uh, review the slides, our previous slides, to ensure that you understand the basic concepts. So it's not to, I mean, ask you guys to memorize formulas, equations in our class. That's really not the goal of this class. It's just to help you review what we have discussed and enforce you to understand the basic ideas.
Awesome. And when is it? Is it on April 30th, that Friday?
It's on the course website. I believe it is the Monday of finals week at
Yes.
like 10:30 in the morning.
Yes, exactly. It should be May 3rd. It should be May 3rd. You can check out.
Okay, great. Thank you.
Yeah. Okay, so let's start. So today we're going to talk about logistic regression. A very it's simple but very widely used classification techniques. Actually, in Amazon, in all kinds of online advertising platforms, you see logistic regression takes the central role. Okay, so before we talk about details, again, let us look at where we are right now, right? So during this, throughout this semester, we have seen quite a few ideas regarding machine learning, right? And from modeling perspective, we have talked about linear models, like linear regression, uh, which is to predict continuous outputs, right? And linear classification, which is to classify the examples into discrete labels, right? And nonlinear models, right? We talk about how to apply kernel tricks or nonlinear feature mapping to extend linear models to nonlinear models, right? And or we talk about how to um, construct a nonlinear models from scratch. The typical one is the artificial neural nets, right? But don't forget, decision trees are nonlinear models as well. Although they look simpler than neural networks, but decision trees are typical nonlinear models. And then we'll talk about the learning principle, namely how do we come out some learning objective, right? So how do we formulate the learning problem, right? So usually we're going to design some learning objective, and then by optimizing that objective, we identify the hypothesis in the hypothesis space, right? So we talk about learning by simply minimizing the loss on the training data, right? This principle is also referred to as empirical risk minimization. Then we'll talk about the problem of that, right? Because it tends to overfit data, right? So when it tends to overfit data, even when the data has some noises, overfitting can hurt your generalization performance. And in addition, even you don't have like harmful noises, if you just want to overfit the training data, you're gonna prefer more complicated hypothesis spaces, which will lead to a smaller generalization error, right? This is the result when we derive the generalization error bound in the agnostic learning setting, right? So a more advanced, widely used, and more widely used learning principle is called regularized empirical risk minimization, right? In addition to the training loss on the data, and we also add a regularization term which penalize overcomplicated hypothesis spaces, right? Like in support vector machines, we add half of the norm, half of norm square of the weak vector, right? Of course, it has some like somewhat deep reasoning chain, right? Because you penalize, you minimize the square loss of the square norm of the weak vector, meaning that you're going to penalize the complexity of the data indexed VC dimension, right? So the smaller the norm, the the smaller the VC dimension, so that the simpler the hypothesis space you use, right? So these are topics and frameworks we have seen so far, right? Today, we're going to look at some example about learning a probability mapping, namely that we're going to do some classification, but we're not directly predicting 0 or 1. Instead, we just map the input instance to the probability that the instance takes the label 1. So the output will be a continuous number between 0 and 1, because we're going to map the instance to a probability. Right? And there is a lot of benefits which we're going to discuss later. And then how to learn this model. Right? We're going to introduce a new criterion. It's called the Bayesian learning criterion. We're going to introduce a map estimation and MLE estimation. Map means maximum a posterior estimation. MLE means maximum likelihood estimation. I guess most of you have heard of those terms before in your statistic class or probability class, right? We're going to just review them. So the specific model we're going to discuss, of course, is logistic regression, right? So we're going to first introduce the model definition of logistic regression and explain the rationale why we're going to model a classification problem by regression, meaning that we're going to predict a continuous value, a probability, rather than just a discrete 0 or 1. And then we'll talk about how to train a logistic regression classifier. Here, we're going to follow the Bayesian learning criterion, as we just mentioned, right? MAP or MLE principle. And finally, we're going to put this Bayesian learning principle in a bigger framework, in the loss minimization framework. So see that actually map estimation corresponds to the regularized risk minimization. If you just do MLE, maximum likelihood estimation, you're essentially equivalent to minimizing the training loss only. It can lead to the overfitting. Okay, so first, what is logistic regression, right? So the setup is as follows. Right? So first, the task or job is to do the binary classification. Right? So we assume that our training inputs or test inputs are d-dimensional vectors, right? So in the d-dimensional input space, and our labels are -1 or +1. Right? Of course, you can use 0 or 1, whatever. Right here, for convenience, we just use -1 or +1. And then suppose we have a set of training data, which are m pairs of xi and yi. Right? So we denote the training data by S. So what does the logistic regression learn? Right? So what does the logistic regression model predict? So we know in our previous topics, right? When we learn linear classifiers, we're going to use some prediction rule, right? We directly, according to that rule, we directly give a discrete label, -1 or 1 over any input vector. Right? But for logistic regression, things becomes a bit different. So instead of predicting the output, we want to predict the probability that this label is 1. So meaning that, okay, so previous, I can give me an example, right? I train a linear classifier, I can tell you, okay, we should label it as positive, right? Otherwise, I should label it as negative. Right? But right now, when I train a logistic regression, I only tell you this example has 0.8 chance to have label 1, or this example has 0.2 chance of 0.2 to have label 1. That's the goal of the logistic regression. So to differentiate the two settings, right? In the original problem, we want to learn a mapping from the input space to a discrete range, right? -1 or 1, right? Now we modify the problem as follows. We want to map the inputs from d-dimensional input space to a continuous range between 0 and 1. Why it is restricted to be between 0 and 1? Because it's a probability. Right? So you can see that because the output now is a continuous number, although it has to be between 0 and 1. So the problem itself is essentially a regression problem. Right? Why? Because regression predicts continuous numbers. Right? That's why it is called logistic regression. Okay, any questions so far regarding the problem setting? Everyone is comfortable? Okay, great. So now I want to ask a question a little bit more in depth, right? So what's the advantage of modeling the classification problem in this way, right? Do you feel there's any advantages or disadvantages? Any thought?
Might give us more range, like it might be more robust to outliers.
Okay. Yeah, that's reasonable.
I think you could also, instead of just predicting the label, and you could now know with how much confidence it's giving that prediction, and so it gives you a little bit more of a layer into what it really is thinking, instead of just if it's yes or no. It gets more nuanced now.
Yes, exactly right. That's a great answer there. Yeah, so that's the major benefit, but this is also associated with what Tusha said, because right now, I just tell you, okay, must be 1 or 0, right? This is kind of a true or right. There's no reflection about your confidence, right? So, but the confidence or the uncertainty is crucial in your practical decision. Like, for example, if you develop some online advertising platform, like right now when you surf on the web, right, nearly on all the pages, right, you will see some like advertisements showing up on some places, right? It's kind of in many cases that you feel it's kind of annoying, but you have no choice. This is the way most internet companies earn money, right? And right now, like most advertisement displacement and the scheduling and all those are done by third-party libraries or third-party platforms, either mainly by Google. Facebook takes a large portion of that market as well. But you see that it's kind of personalized. They're gonna look at the features of those web pages, and perhaps if you allow cookies to track your profiles, they're gonna integrate your personal features into that model. And the typical model, they might have a lot of models, right? Typical model is a logistic regression. They're gonna predict for this particular advertisement, you're gonna click them or not. And the more accurate they can predict you click or not click, the more money they earn. And even increase 0.1% of click-through rate prediction, they're gonna earn like millions of dollars or billions of dollars every year. So it's a huge market. It's a huge market. So, but there's always a kind of like trade-off question. So they can, according to the history data, right, they can predict if you like it or not. Right? But there's a trade-off. Like if you always push something you kind of familiar with, people or users will feel tired very soon, right? So there's a trade-off, like so-called exploration or exploitation. They want to have some mechanism to push some fresh things, fresh advertisement to you, so that you will like it. So, and then how do we decide we're gonna use exploration of your past history, or they're gonna push some fresh things? That is uncertainty or the confidence level. If my model tells me, okay, for this particular person, when I show this advertisement, he or she will have like 99% accuracy or confidence to click that advertisement, to like that advertisement. Okay, I'm gonna use my model, right? Because I'm pretty much sure they'll click that. When they click that, it is likely to bring purchase behaviors and profit. However, if my confidence is not that high, like okay, I only have 60% of confidence, and then I need to think about, is it worth to showing those old style advertisement, or should I push some new content? So nearly all the modern online advertisement system has such kind of design mechanism. Of course, it's much more complicated than the example scenario I explained here, but they always have some problem. They need some like confidence levels, uncertainty to help the system to make the decision. So of course, if you use logistic regression, they're gonna give you such a score. Okay, so any question regarding the setting? Okay, now that everyone is comfortable, let's proceed, right? So obviously, if you want to just map some arbitrary input vector to a probability, right, between 0 and 1, right, there can be many hypothesis spaces, right? And here we're gonna introduce how logistic regression model assumes this regression model, right? So they're gonna use the so-called Sigmoid function. So I think this is not weird to everybody, right? Everybody has seen this when we talk about artificial neural nets, right? So the hypothesis space for logistic regression is like this. We assume the prediction function is just a logistic function or sigmoid function. So they're the same thing. Right? So for any input x, to calculate the probability x has label 1, we're going to first introduce a weight vector, w, right? Of course, here we assume x has already been augmented with a constant feature 1, so that the weight vector w includes a bias parameter. So this is very similar to the linear model definition, right? And then we're going to perform some sigmoid transformation like this to ensure that your output is always between 0 and 1. Right? We mentioned, we discussed this activation function before, right? So it will map any value between 0 and 1, and later we'll see the function curve. So to summarize, right, any hypothesis in logistic regressions hypothesis space is a linear function composed with a sigmoid function, or in other words, logistic function. And the output of this logistic function is our regression value, namely the probability that the input x takes the label 1. Right? So this is a reasonable choice, and we'll see why. So now I want to ask, right, what is the domain and the range of the sigmoid function? Right? We know the range is between 0 and 1. What is domain? What is the possible input values to a logistic function?
Wouldn't that be just all real numbers?
Yes, exactly right. That's why we favor logistic function, because it does not restrict the input. And even better, it's going to map arbitrary input in the real space, right, in the whole real life, right, to a number between 0 and 1. Right? So don't worry about, okay, if your output is valid or not. There's valid probability now. Right? So now we can take a look at the curve of the sigmoid function. Of course, here we haven't integrated into the inner product between the v vector and the input vector. Right? We assume, okay, the input is just a scalar z, right? So you can see that when z equals to 0, the logistic or sigmoid function will give the value 0.5. And the larger the z, the closer the sigmoid function value to 1. The smaller z, meaning that when z approaches to a negative infinity along this direction, then the sigmoid function value is approaching 0. So it's kind of like squeeze a real number to a range between 0 and 1, and the sigmoid function is also a monotonic function. And someone asked, okay, if there is any other function can do the same thing, the answer is yes. For example, another commonly used model is called a probability model. They replace the logistic function here by the Gaussian CDF function. It's called cumulative density function. I assume everyone knows that. And they have a similar curve like that, but they have a discrepancy in this region, -2 and 2 region. They have a little bit different behaviors. But logistic regression perhaps is the most widely used choice. Okay, so let us review the nice property of the sigmoid function. Actually, you haven't discussed before, right? So when we take a derivative of the sigmoid function, this sigmoid function, 1 over 1 plus e to the power of minus z, right? So when we take derivative, what can we find, right? Let us do this again, right? So you take derivative, you can view this whole as one part, right? Apply the chain rule, so it is minus 1, and then the denominator will take square, and then you take derivative over the denominator, and which is take derivative over the exponential term, which is to take derivative over minus z, right? You have a minus sign from here, you have a minus sign from here, so they cancel. So I'm just so it's essentially if you write down everything, right? So if you take the derivatives of 1 over something, right? So it's gonna be minus 1 over the denominator, take the square, right? And then apply the chain rule, you take derivative of this one. So it is essentially, it is going to taking the derivative over this exponential term, which ends up with exponential term, then take derivative inside this exponential, you have a minus sign, again, right? So you see the two minus signs, they cancel. They give a positive, right? So the key observation is here. So the numerator is exponential to the power of minus z. The denominator is a square of this 1 plus e to the minus z, right? So if you write it down as a product explicitly, so this is essentially the first one. We remove here, so and you put 1 here, right? So this part is just this, is just the sigmoid z, right? And this part, like exp to the power minus z in the numerator, and the remaining one denominator 1 plus exp to the power minus z. So it is equivalent to 1 minus 1 over this denominator, which is 1 minus sigma z. So we have done that before, so I don't need to repeat that. I think everybody should be comfortable with this. So the good structure of the duality of the sigmoid is that, okay, it is just the sigmoid multiplied 1 minus sigmoid. So from this we can say it is always the negative. That's why we see the function curve for sigmoid is monotonic increasing. Why? Because its derivative is always non-negative. So now, according to the logistic regression model, right, we can model the probability when you take label 1 to be the logistic function of W transpose X, right? So if you substitute W transpose X into the logistic function, you get this, right? And similarly, right, when you take 1 minus y equals to minus 1, right? So you are actually subtracting 1 by the sigmoid function, right, which is this, right? And you divide this exponential term on both numerator and denominator, you end up with this, right? So you can see they have a very similar form, right? Except that for taking the probability, for the probability taking y equals to 1, you have a minus sign in front of it. Right? For taking minus 1, we don't have minus sign in front of this W transpose X. Right? That means we can simply unify the two expressions together, right, in one expression. Right? So we just use one expression to represent the probability given X and W taking the label Y. So we can check that if Y equals to 1, right, so you recover this, right? If Y equals to minus 1, you recover this. So this will be much more convenient, right? You don't need to consider two branches. Any questions so far? Is everyone good? Okay, so as we mentioned before, right? So we know that, okay, given us a probability, we'll leave some confidence levels, right? But given this probability, we still need to make decision, right? We need to decide if I'm gonna classify this example as positive or negative, right? So then what is a commonly used rule to determine the final label given a predicted probability? So a very commonly used rule will be just to look at this probability, right? If it's bigger than half, 0.5, then we're gonna predict X with label 1, right? Otherwise, we're gonna predict the label as minus 1. So now I want to ask, what that this rule corresponds to in terms of the inner product between W and X?
0? Greater than 0?
It can be a little bit more specific. Just a little bit.
So W transpose X should be greater than equal to 0.
Yes, exactly right. So if we can translate this rule in terms of W transpose X, right? So it is equivalent to looking at W transpose X, right? If W transpose X is bigger than 0, then we know that this score must be bigger than 0.5. Then we're going to predict X as 1, right? If W transpose X less than 0, right? Less than or equal to 0. So we know that this exponential value will be less than 1, right? So 1 over 1 plus some value less than 1 will be it will be bigger than 1 because W transpose is less than or equal to 0. So the minus W transpose X will be bigger than 0. And then this exponential term will be bigger than 1. The 1 over 1 plus some value bigger than 1 will be less than 0.5. Right? So that means we're going to predict X as negative. Right? So now we can associate this rule with the previous prediction rule we have used many times, right? When we talk about classifiers, linear classifiers, we're kind of always using this rule, right? We just look at the sign of the W transpose X, right? If it is positive, and we take the sign, we make the label positive, right? We predict the label as positive. If it is less than 0, the sign -1, the label is -1, right? So they are equivalent. And they're both equivalent and reasonable, right? In practice, I mean, logistic regression here gives us a more flexibility. So for some applications, you might have like a even higher threshold to give 1 because I want to reduce the chance of false positive, right? So I may set up the threshold to be the probability threshold to be 0.8, right? I only, when I look at the probability to be bigger than 0.8, I'm gonna give the label 1. Otherwise, I'll give the label to be 0. In this case, I can avoid false positives because in many applications, false positive might be, very bad. But without any prior knowledge or any domain knowledge, 0.5 is the commonly used threshold, and this is equivalent to the previous prediction rule we have used. Okay, any question? This is about how do we, according to the prediction of logistic regression, to make our final decision for the labeling. Okay, so now we have introduced the definition of logistic regression model, right? So we next talk about how to train a logistic regression. So first, we're going to talk about maximum likelihood estimation. And then we'll talk about, we're going to add some priors over the weights of the logistic regression, and then we maximize the data likelihood and as also the prior, which end up with the so-called maximum a posterior estimation. And finally, we'll relate them to the loss minimization framework. Okay, so again, let us get back to the problem of learning first, right? So here is our training set, right? We assume our training set consists of m examples. Each example corresponds to a pair of the input example and output label, yi, right? So how do we formulate learning? Right? In the logistic learning, we want to find a V vector, of course, including the bias parameter, such that the probability given this V vector W the labels are maximized. Why? Because we have some model, right, to model how likely each label yi taking the corresponding, each output taking the corresponding label given the input xi, right? So this is a probabilistic model. So now if I want to find out the optimal weight vector, we're gonna find a weight vector that maximizes this labeling probability. So this is called a maximum likelihood estimation. And of course, we assume that our examples are drawn independently and identically from the unknown data distribution. And now how do we proceed? Let's first write down the joint probability, right? So given the weight vector, what are the probability of those M labels? So because they are RID, right, identically independent identically distributed, so the joint probability is written as a product of the probability of each label yi given the input xi and given the feature weight vector. And then our problem becomes maximizing this joint probability with respect to W, right? When we optimize this probability, we find the optimal weight vector W, right? This is called maximum likelihood estimation. Any questions so far? I believe everybody has knows this concept, right? Maximum likelihood estimation. Okay, so but here from computational perspective, there is a problem here. So we know that this is a logistic regression, right? This is actually some sigmoid function of W transpose. Sorry, it's not. It's W transpose xi and then times yi, right? So this value is strictly between 0 and 1, right? The sigmoid function value, so it's a probability, right? So when you multiply many values between 0 and 1, it will be easy to approach 0, right? So it's very easy to make numerical underflow, meaning that, okay, when you multiply this together, you don't have enough digits to store the precision, and then you just truncate your probability is truncated to be 0, and then you cannot apply any optimization algorithm to optimize W because you're taking gradient with respect to 0. You're taking gradient over 0, right? So it's gonna still be 0, right? So the most commonly used trick is to avoid directly dealing with probabilities because they're so small. So we're gonna convert these products to sums by taking logarithm. Right? And why is this valid? Because log is an increasing function. So if you maximize the logarithm of some function, so the maximum doesn't change at all. But numerically, it will be much more stable, right? So when we take a logarithm in front of this product, we know that it immediately becomes a summation over the M training examples, where each summand is the log probability of the label yi given xi w and w, right? This is actually a log sigmoid function, right? So by definition, we know that P of yi given wxi is a sigmoid yi w transpose xi, right? If you just write down the sigmoid function explicitly, it will be look like this, right? So now we take a logarithm over there and write down the objective function. It becomes this, right? So maximum from 1 to m, and each summand is negative logarithm 1 plus exponential to the power of 1 minus yi double transpose xi, right? So this is a direct results when you take log in front of this, right? So you have a 1 over this. So it's essentially this denominator take the power -1, right? You take log, you put the power in front of the log. That's where you have minus sign in front of it, right? You maximize it, so this is equivalent to minimizing, but minimizing the negative objective, right? So 2 negatives now becomes positive. So you're minimizing this summation of the log values. Any questions so far? So now we have formulated our learning objective for logistic regression, right? So what's the next step? Any thought? What is the next step?
Gradient.
Yeah, and using gradient for what?
Calculate the update on W. So we'll start with some W, and then
Yes.
add the gradient.
Yeah. So this now comes to the general framework we discussed again and again, right? So we have formulated a objective function, right? So the learning becomes minimizing that objective function with respect to our model parameters. Then we can just use the gradient descent framework to minimize this objective to find optimal weight vector, right? So most commonly used framework is the stochastic gradient descent, right? So you can see that the goal is to maximize the likelihood to train a probabilistic classifier under the logistic regression model. To maximize likelihood, we maximize the log likelihood, and of course, we minimize the negative log likelihood, right? So the remaining thing will be minimizing this, right? So this one is also called logistic loss. So you can see the connection between the probabilistic formulation and non-probabilistic or frequentist point of view, right? So people who are not doing probabilistic learning call this is a logistic loss. Okay. So before we proceed, right? Before we proceed to like the details of the gradient calculation and then how to plug them into the stochastic gradient descent framework, which everybody has been familiar with, right? So let us consider a more advanced, a more popular framework on top of the MLE, or maximum likelihood estimation, which is called maximum a posteriori estimation. So remember, in the maximum likelihood estimation, okay, we just model the likelihood of the data, right? So given the weight vector, how likely each xi takes the label yi, right? We just maximize that likelihood. So now we want to also add the prior on the weights. That needs us to think more in a probabilistic way, like from a Bayesian perspective, a probabilistic perspective, we're gonna first sample the regression weights from some prior distribution. And given that weights, we're gonna sample each label from the logistic likelihood or logistic function. And what prior distribution do we use for the weights? The most commonly used prior is the normal distribution. So assume each weight in the weight vector is drawn independently from the normal distribution with zero mean and some standard deviation sigma. So I believe everybody is familiar with the normal distribution, right? So that means we can write down P of W, which denotes the prior of the weight vector, as a product of the prior over each particular weight element, right? And each particular prior is a scalar normal distribution with mean 0, right? And standard deviation sigma. And now
we are initializing the weight vector, or what's a prior?
The prior is can you say it again about your question?
Yeah. So are we initializing the weight vector using the normal distribution, or what?
No, we're not initial the. We're still talking about modeling. We're not initializing the weight vector by drawing some sample from this normal distribution. It's not like that. We just assume, okay, from modern perspective. So remember, as we just talked about, logistic regression is essentially modeling given the weight, how do we sample or generate the label, right?
Right. Okay.
From logistic function. Right now, I just want to add one more component. How do we sample the weight vector?
Okay. Gotcha. Thank you.
Yeah, so that I can write down a drawn distribution about the weight vector and the labels. And then we're gonna estimate our model based on this drawn probability. Okay.
Perfect.
So now we can see that in our previous maximum likelihood estimation, right? We just model given the weight vector, how do we get each label in the training set, right? So maximize this label's likelihood, it is equivalent to solving this, right? But right now, in this new criterion, right, we're gonna also model how the weight vector are generated. Right? So we assume, okay, they're gonna sample from a normal distribution with zero mean and the standard deviation sigma. Right? So, and then we want to maximize the joint probability of the weight vector and all the labels. That's the new idea, right? So compared with the maximum likelihood estimation, we have one more component that is about the weight vector, right? So right now, we're gonna maximize the probability of the prior probability of the weight vector and the probability that each label given the input and given the W, right? So jointly maximize this probability or this joint probability. So if we estimate W by jointly maximizing this joint probability, this framework or this idea is called maximum a posterior estimation, namely map estimation. Why it is called map estimation? Because if you calculate the posterior of the weight vector, given the trained data, it is proportional to the prior multiplying with the data likelihood, right? Of course, if you want to write down explicitly, you have to divide this product by the marginal likelihood of data, right? Which is constant to the weight vector W, right? So actually maximize this product is equivalent to maximize the posterior probability of the weight vector given the data. That's why it is called maximum a posterior likelihood, maximum a posterior estimation. Any questions so far?
The main assumption here is all we're changing is we're saying, and so in the MLE formulation, we're saying we want to maximize the probability of S given W.
Yes.
But in this case, now we want to maximize P of W given S and the way we get that is by now we have this joint probability where we're now incorporating the probability that the weights are going to be drawn from this normal distribution.
Yes.
Okay.
And it's a nice connection to the posterior. Why? Because this drawn probability is, the posterior probability of W given S is a normalized version of the joint probability. And the normalizer has nothing to do with the weight vector we're interested in, right? So maximizing this joint probability is equivalent to maximizing the posterior probability. So that's why it's called maximum a posterior estimation. And conceptually, it will be more attractive. Why? Because it considers everything in a posterior space, right? If you're doing Bayesian, okay, I have some prior which integrates my prior knowledge. I have some data which integrates the knowledge I have observed. I'm gonna integrate them together, and the integrated together is represented by the posterior distribution. Now I want to maximize the posterior distribution, the posterior probability, meaning that, okay, I can effectively integrate both the prior and the observed knowledge. But later we'll see that, okay, this also relates to the regularized empirical risk minimization framework in the non-Bayesian or non-probabilistic domain. Okay.
Can we say that map estimation, if we assume that the probability distribution of W is uniform, then it will be MLE?
Yeah, yeah. I guess you're saying the maximum likelihood estimation can be viewed in that way, right?
Yeah. Like
Yeah, you're right. You're right. Yeah, that's kind of like a widely recognized by the statisticians, right? So you can view maximum likelihood estimation as a special map estimation where you put a uniform. Sometimes it's also called like uninformative prior distribution, meaning that the prior of the W is proportional to 1.
Yeah.
Okay. So now let us look at how do we deal with map estimation, right? So we know that maximize the posterior probability of W given the training data S is equivalent to maximize the prior multiplying with the data likelihood, right? And again, we're gonna take logarithm to simplify this, right? So we do not need to deal with the product of many small numbers. So it is equivalent to maximizing log of the prior of W plus log of the probability of the labels given the weight vector W, right? And now if we expand them, we know that the log P of S given W is here, right? And for log prior of W, right, we just take logarithm of those normal distribution, right? If we take a logarithm of this product of normal distribution and then throw out those constant, right? So sigma square root 2 pi, they're all constant to W, right? So only need to preserve logarithm of this exp. So you have minus Wi square over sigma square here, right? Left in the logarithm, right? And this, of course, you need to sum them from the first weight to the least weight to the final weight, right? So this now because it becomes our objective for map estimation. If you look at compare with the MLE, right? Maximum likelihood estimation is here, right? So only have some terms related to the prior, right? And this term resembles SVM, right? So remember, in our SVM formulation, we have regularization term. In addition to the hinge loss, we have regularization term that is half of the W transpose W, right? But here we have a 1 over square sigma square W transpose W, right? Of course, if you multiply sigma square to this side, that means you have this. You have W transpose W multiplying with some constant, right? You have some hyperparameter multiplying with the logistic loss. Right? This is where it has the same position, or it's kind of a counterpart to the SVM hyperparameter C, right? It's a trade-off between the regularizer and the loss.
It looks like in this equation we're missing the closed parenthesis for the log. Is that supposed to be after the exponential?
Yeah. This is a typo.
Okay.
Yeah, sorry. This is typo.
Yeah,
That's for
no
point
problem,
out.
thanks.
Yeah, definitely. Yeah. Okay, yeah, I actually add this parenthesis here, right? So you can see that this is logistic loss, right? So this is a prior, log prior, which corresponds to regularizer, right? If you multiply sigma squared to in front of both terms, right? This one disappears, and this part is in front of this data loss. So it actually has the same position as the constant C in the SVM loss. So now we can see there are kind of a strong connection, although they are formulated in different frameworks. So again, maximizing this negative function is the same as minimizing the function, right? So you can just get rid of this minus sign and then change max, switch max to the mean, right? So now we get our final objective for learning logistic regression model with map estimation. So where have we seen this before? It's the fallback machines, right? And the other, the regularized imperial grace framework. Right? So now we have saying what is the objective function, what is the optimization formulation for both maximal likelihood estimation and map estimation, right? Next, how do we solve that? Like, how do we solve this problem in our favorite stochastic gradient descent? Before we proceed to the details, right? So I want to mention that historically, there are many other training algorithms as well, like LBFGS. If you haven't used in your homework before, right, you should be familiar with that, or any quadratic optimization problem. That was widely used when your data set is relatively small, right? But nowadays, the data set you met is often like hundreds of millions or even billions. So the most favored approach will be based on stochastic gradient descent. So now I want to write down the framework, the stochastic gradient descent framework for training logistic regression as a guidance for you to implement in your homework. But this is also a review for everybody for this for the stochastic gradient descent framework again, right? So let me stop sharing. I'm gonna switch to the whiteboard. Can you see the whiteboard?
Yeah.
Okay, great. So so before we write down the algorithm steps, let us just do a little bit. Sorry, there's extra parentheses here. So a little bit gradient, right? So because you have to do it by yourself, right? We can go through it together, so you won't be confused. But I think it should be simple to everybody, right? So remember, this is a logarithm of log of this, right? So it is 1 minus log 1 plus this exp.
Sorry, we're not seeing your writing.
You can't see my writing?
No.
Oh, that's bad. Can you see the transition?
No, it seems to be frozen.
Oh, I see. Wait a second. Why it is paused? Let me do it again.
There we go. I think that'll work. I see there. Yeah, that looks great.
Oh, nice. Okay. Okay. So if you look at this logistic loss, right? So it is essentially minus logarithm 1 plus minus yi w transpose xi, and then you take power of -1 here, right? So they are equivalent. These two are equivalent. Why? Because this is power of -1, right? So you take a logarithm, you move -1 in front of it, so they cancel with minus sign in front of it, right? So why should I write things like that? Because this part, take -1, take power of -1, is sigmoid yi w transpose xi, right? So now if you want to take the derivative, right? If you want to take the derivative of this, we just apply the chain rule and the knowledge we have used, right? We have discussed, right? So if you're gonna first take the chain rule, sigmoid, right? And then take the derivative over the sigmoid, and we know that the derivative of the sigmoid is sigmoid multiplying with 1 minus sigmoid, and then apply the chain rule. You're gonna take the derivative of this term inside, which is simply yi times xi, right? Because it's w transpose xi times yi, right? So now you can see the gradient of this logistic loss is very simple. The form is very simple. It's -1 minus sigmoid yi xi. Okay. So hopefully, when you derive your gradient and when you apply it, implement your own logistic regression, you won't feel this is too complicated. Okay. So now let us just try to write down the stochastic gradient descent framework, right? So again, we assume our data as is just a pair of these xi, yi. Suppose we have m training examples, right? We know each yi is either -1 or +1, right? So in the very first step, we're going to initialize our weight vector. So remember, the weight vector consists of this feature, width, and the bus parameter, right? So I do not need to write down explicitly, I believe, right? And then we're gonna go through the whole data sets for big T epochs, right? So this is a hyperparameter which you need to pre-specify, right? And then inside each epoch, you're gonna randomly shuffle the data sets, right? It's just to increase randomness to improve the to improve the robustness of stochastic gradient descent, right? And then for every incoming training example, say xi, yi, we're gonna construct a stochastic objective, right? How do we construct it? We compute the logistic loss, right? So which is a logarithm 1 plus exp minus yi w transpose xi, and then we need to multiply it with the total size of the trained data, right? And then plus, sorry, I need to plus this regularization term, right? As to why we should duplicate these examples for m times and then calculate the loss on the duplicated data set, we discussed before, right? Only doing this, your stochastic objective is unbiased estimate of the true objective, meaning that if you take expectation of this is the true objective, right? And then when you calculate the gradient of the stochastic objective, your stochastic gradient is unbiased. And then we have all kinds of theoretical guarantees, namely by choosing a right schedule of the step sizes, it will converge to some minimum with probability 1 or almost surely, right? So then, and once you get this stochastic objective, you calculate the gradient, right? And you use this gradient to update the weight vector. That's it, right? And then you need to choose a gamma t, right? So we know that we have quite a few schedules of gamma t's, right? So we know that they have to be diverge for the summation, but the square summation must be bounded, right? And that's it. And finally, after you finish all the big T epochs, you can return W, right? Okay, any questions so far? I assume everybody is comfortable, right? Everybody has been very familiar with this framework, right? So now what you need to do is just replace the stochastic objective by the logistic loss, right? And then calculate gradient, and then plug in. Okay, so now we need to go back to the slides again. Please bear with me. Can you see the slides?
Yes. And the transition looks good.
Okay, great. So now we have finished the introduction of the logistic classifier training, right? It's actually pretty standard, right? What you need to do is just, okay, you know the trick to compute the gradient, and then you know how to correctly apply the stochastic objective and calculate gradient and apply them in a stochastic gradient descent framework, right? The framework itself is pretty standard, right? So now let us go back to the loss minimization and try to find some connection with the previous loss we have seen, right? So previously we have discussed, right? We can formulate any machine learning problem as a loss minimization problem, right? So the general setup is that we assume our training examples are drawn from some fixed, unknown distribution data, right? And of course, we assume there are some hidden Oracle classifiers that give the ground truth label for each example. And our goal is to find a hypothesis H in our specified hypothesis space that mimics this target function F. Right? So in the ideal case, right, how do we define a loss function L that penalizes bad hypotheses, right? Because the learning procedure is essentially searching procedure, right? So we're gonna use training data to guide our search. We want to penalize those bad hypotheses and to get rid of them, and then we can locate and find our best hypothesis in the hypothesis space, right? So ideally, we want to pick up some function that in a hypothesis space is essentially pick up a hypothesis in a hypothesis space that can minimize this expected loss. That is, we compute the loss of the prediction made by this hypothesis and the ground truth label made by the target function, right? And we want to minimize the expectation with respect to the data distribution, right? This is the ideal situation. However, the data distribution is really highly complicated. It's really unknown, right? So we need to compromise a little bit, right? So suppose we just collect a finite number of training examples, then I minimize the average loss over each training example, right? So this is called empirical loss. Why this is called empirical loss? You can view it as, okay, I use the training data points, right? X1, X2. So suppose I have M training examples, right? If I use this M training examples to construct empirical distribution, they can approximate the unknown data distribution, right? So in statistical theorem, empirical distribution means that point masses over those training points. And when your number of training examples goes to infinity, then empirical point distribution will converge to the ground truth data distribution. So that's why it's called empirical distribution. And then the loss constructed based on this empirical distribution is called empirical loss, right? Because this can be seen as you're taking expectation of the loss under empirical distribution. So that's where this empirical loss comes from, right? So, but just minimizing an empirical loss on the training set has some problem. What is the problem? What is the problem? Any thought? We actually have mentioned before, right? What's the problem? If you just minimize the loss on the training set.
Might go to 0.
Yeah, goes to 0 means what?
It means we might not be very good at generalizing. We'll overfit.
Yes, exactly, right? So the major issue is overfitting, right? Overfitting has two consequences. First, if the data has a lot of noises, right? We have mentioned when discussed that phenomenon in a decision tree topic, right? It will hurt your generalization performance because you overfit the noises, right? The noises will mislead your learning procedure, right? To find better hypothesis. Right? On the other perspective, even you don't have any noises in your data, right? And if you still focus on minimizing the training loss only, right? You're gonna choose more complicated hypothesis space, right? Because complex models tends to fit the data better. And as a result, you have much more risk to have larger generalization, right? This is reflected from the generalization error bound we discussed before, right? So we know that the true error is bounded by the training error plus some term determined by the VC dimension, right? So VC dimension is an indication of the complexity of a hypothesis space, right? The larger the VC dimension, the more complex the hypothesis space means that the larger the generalization error bound, meaning that you have a large risk to have a bigger generalization error, right? So that means only minimizing empirical loss is not sufficient, right? You either will be affected by noises, will be misled by noises, or favor complicated hypothesis space. How should we do that? Right? So a solution will be to add a regularizer, right? So in addition to minimizing the training loss, we also need to minimize a regularizer. This regularizer will penalize the complex hypothesis spaces. That's the typical example is the support vector machines, right? So in the support vector machines, the loss is a hinge loss, but the regularizer is just a half W transpose half, right? It actually has a direct association to the VC dimension, right? Data-dependent VC dimension of the linear classifiers, right? So in general, we can say we're going to compose our objective function as two parts, a regularizer plus a training loss, right? We're going to find the best trade-off between the two. And oftentimes you need to specify a trade-off parameter constant C, right? So this is for linear classifier, right? So this is a so-called regularized risk minimization framework, right? So it is more robust. It has the flexibility to penalize overcomplicated hypotheses so that it is more likely to give you better generalization performance, right? So when we talk about loss function, right, we know that loss functions should penalize mistakes, right? If you use if your prediction is far from the ground truth, you have more cost. That's why, or more cost or more loss. That's why it's called loss function, right? And we usually define the training loss as the average loss over the whole training data, right? But then that brings a question, right? Is there any standard, or is there a golden standard for the loss function? The answer is yes, right? Ideally, the standard or the golden standard of the loss function is called 0-1 loss. So it simply only penalizes mistakes. Right? If your prediction is wrong, I give you a penalty or give you loss 1 or arbitrary constant, right? You won. And if you make a correct prediction, your loss is simply 0. Means that you do not need to suffer from any loss, right? And for linear classifiers, we can use this testing condition, right? Y, the ground truth label, multiply this prediction score, right? If it is less than or equal to 0, then the loss, the 0, 1 loss is 1, otherwise it's 0, right? However, this is simply ideal and the golden standard. We cannot directly minimize 0, 1 loss. Why? Because it is intractable. It is not differentiable, right? If you add up, it is actually a set of indicator function of if your testing condition is satisfied or not, right? If you write it down, you cannot take gradient, and what you can do is just combinatorial search. This is it's really hard to optimize. So in practice, we often need some surrogates. That surrogate usually you can calculate some gradient or subgradient, and so that you can effectively or efficiently optimize the weight vector. That's where we have seen so many loss functions, right, so far, right? So here is a zoom of the loss functions we have seen, right? So perception loss, we mentioned before, right? Your mistake-driven updates of perception is essentially to minimizing some loss, right? And hinge loss comes from spam formulation, right? Exponential loss from eta boost, and the logistic loss from negative log probability of the label y taking 1, right? And if you contrast them if you contrast all kinds of loss functions in terms of their curves, right? You will find some interesting things, right? So this is a 0, 1 loss. So this is a golden standard, and it is ideal, but it's very hard to optimize. So we have many other surrogates, right? Like hinge loss, it is essentially an upper bound of the 0, 1 loss. And perception loss is not upper bound. And exponential loss is another upper bound. In the boost, right? Is another upper bound. And here's the logistic loss. And different loss will give you different capabilities. From probability perspective, from the statistical perspective, people have developed a lot of theorems to characterizing in what kind of sense the estimation from different losses will be consistent with the 0, 1 loss. So this is a very theoretical direction in machine learning and statistics. Okay, so we have finished the introduction of logistic regression. To summarize, logistic regression is a classifier that predicts the probability of the label being 1. It's not to predict the label itself. It's to predict the probability of the label. So it is a discriminative classifier that can be trained while map estimation or maximum likelihood estimation. And in the next class, we'll talk about the general principle for Bayesian learning, and we'll revisit map and MLE principle again. And it is a discriminative classifier that minimizes the logistic loss over the training set. This is from the loss minimization view. Okay, thanks everybody. So we'll stop here and see you on Thursday.
So I just have one kind of follow-up question then with the lecture. So really what you've shown is that really all of the linear methods that we've learned are all basically, it's the same. Obviously we're trying to solve the exact same problem. It's just that we can use a variety of loss functions to help us be able to learn some classifier. And you've shown in that graph there, we have this wide variety of kind of approximating this gold standard, the 0, 1 loss. And so really so when we've learned each of these algorithms, it's basically just saying, well, if we pick a different loss, how do you minimize that loss? And that's
Yes.
literally what all of the algorithms have been.
Yes.
Cool. That's really cool that it's like unified in that way.
Yeah. So actually, you'll see actually different machine learning models just correspond to different losses. Of course,
Right.
a lot of different ways to solve that loss to optimize the loss function.
Right. And that's, yeah. Cool. Cool. Thank you. That makes a lot of sense.
Okay. Okay. If you have a question, just give me 5 minutes. I need